Yeah, you can see my screen, right?
Yeah. Okay, go ahead. Yeah.
Okay.
Vishnu.
Yeah. So basically today I'm going to talk about first principles electrical conductivity calculations, and I'm also going to give some brief updates about our work on the energy comparison between different DFT codes, between VASP, MUST, and WIEN2K. I'd already given a talk on that previously, and so quite a lot was covered in that. So in this at the end of this talk, I'll just give a few updates on what we have done since then. But first, this talk is to discuss basically some of the work that was done during the summer when I was interning at Oak Ridge under Marcus Eisenbach. So just to recap, the Kubo-Greenwood equation, as is presented here, is a very useful way for us to calculate electrical conductivity within the KKR formalism, because you can convert equation 1 here, which is in terms of wave functions and current operators, into Green's functions, specifically the imaginary part of the Green's function. And in the KKR method, the imaginary part of the Green's function is quite easily available. So we can implement equation 2 in MUST, and it has been implemented in MUST, and that allows us to calculate electrical conductivity from first principles. So basically how it's done is you can modify that equation that I just shown into a form given in equation 5 here, where the Green's function is in terms, you can write it as in terms of multiple scattering operators, which is tau matrices. And you can then get something like equation 5 here, where you essentially need current matrices and you need the multiple scattering matrices, and then you can put them together, and that will give you your conductivity. And generally, what we mean by conductivity in the math is sigma tilde, and it's then implied that the process, you would calculate sigma tilde at two energies just above and just below the Fermi energy in the imaginary plane. So epsilon f plus I delta and epsilon f minus I delta. And then you would calculate this limit here. And that would give you the conductivity. And basically, like in the code, calculating limit essentially means that you just put a small value of delta, which you would specify in the input file. And generally, I found that specifying delta as 10 to power minus 4 seems to be a good choice.
So Vishnu, this is now scattering because of the disorder when you have an alloy, right? If you had a periodic crystal, then you wouldn't get any scattering here, right?
Yeah, so I mean, you can calculate this for a periodic pure element crystal, and you would find that this would go to infinity. Yeah, and I have some calculations that show that. So
yeah, the reason I'm asking, I've seen some calculations where people do, for example, you can do molecular dynamics, DFT with molecular dynamics at finite temperature, and then the atoms start to move around. Right? And then for each configuration, you can do a DFT calculation, and then there will be displacements of these atoms due to thermal fluctuations treated as static. That will give you an additional form of scattering, and you can think of this as phonons, right? Which can be done similarly here. It's just the question how you compute your scattering matrices, right?
yeah, that's true. Yeah, so basically, if you have a pure crystal and everything is in the correct lattice side and there's no randomness, this sum, so there is a sum over M and N. So that sum will just not converge. It'll just blow up. Okay, so now, as mentioned, we are dealing with random alloys. So if you see these brackets, angular brackets here, they refer to an ensemble average, which is how we would deal with the randomness. And how we would study the conductivity of such systems of alloys where there is a random chemical species distribution. There are broadly two methods. The first is the effective medium approach, or CPA, where you don't deal with individual configurations. You take an effective medium that would mimic the ensemble average of your random system. So within CPA, you can modify. Basically, there is quite a bit of algebra given in this paper mentioned below by Bill Butler, and that entire paper, he basically shows how you can go from this Kubo-Greenwood expression of tau to something that instead deals with concentrations. So the idea is to then convert this sum into an integral, this product of tau integral over the Brillouin zone. So you would calculate the CPA medium, and you would calculate the tau matrix in the CPA medium, and then you would calculate this integral here, and then you would take the species average instead of an individual site sum. So this is a sort of well-established theory, and there have been several studies since this 1985 paper where people have used this technique to calculate the electrical conductivity of a random alloy. And I'll show one example that we did recently, which is the aluminum doped cobalt chromium iron nickel high entropy alloy. And this has an interesting phase behavior because at low aluminum concentration, this is FCC, and you see the resistivity rising steadily. But then as you reach an intermediate aluminum concentration, there is an FCC BCC mixed phase, and there is a drop in the resistivity. So there is a non-monotonic behavior, which is interesting. And then as you get to higher and higher aluminum concentration, it becomes fully BCC. And then you get back your increasing monotonic behavior.
Can you just explain what is the mixed phase? How is that treated within CPA?
Yeah, so I'm getting to that. So basically, what we did is we calculated those two phases separately because so we calculated the FCC and we calculated the BCC. We took the lattice constants and what the actual concentrations, the experimentally observed concentrations from an experimental paper that we found, and we just put that value in, put those concentrations in CPA. We built an FCC structure, BCC structure, calculated the resistivity, and basically looked at how it varies. And the interesting thing we found is, so the FCC shows just a plateau in the multiphase region, and it has nothing remarkable there. But the BCC resistivity very closely mimics, qualitatively closely mimics the trends seen experimentally.
Very nice. Very nice.
Yeah.
So the physical, if I understand correctly, because you've done the parallel and the series average, the physical picture, if I understand correctly, is that you may imagine these domains, that there are crystalline phases with big domains. That these domains are so big that you can really treat it as a random resistor network. And then these resistors, they can be either in parallel or series, but in fact, one could also, another thing that one could do, which is kind of neither parallel, neither average, is when people have random resistor networks and they're random, so they are neither parallel nor series, then there is a percolation theory that one needs to employ. And in particular, there is an effective medium approximation in percolation theory that, can be, one can actually put the resistivities of each component of the mixture and get a result. So I assume that, I think it would be sort of interesting to see if you actually, rather than doing parallel and series, if you actually did in some way this percolation theory more consistently, probably presumably because these two are very similar, you'll get something similar to that as well, but more justified perhaps, right?
Yeah, that's true. So initially we thought we would have to do something like that, but then when we saw that the BCC actually pretty closely resembles experimental, so the conclusion we came to is that the BCC is having the dominant effect here.
I see.
And in fact, when we looked at so there's a nominal concentration of the two phases, which is what you set it to be, and then when you experimentally measure the concentration of the two phases, from the experiment data, it seemed that in the multiphase region, the FCC concentrations don't really change. So whenever you add more aluminum to the system, it seems to affect only the BCC phase.
But do you actually understand why is it that the BCC by itself is closer to experiment than the mixture? You think that it should be the other way around, right? That if you have some fraction of FCC, that should, you know, make it closer to experiment rather than the opposite. That's kind of bizarre.
Yeah, we're not fully sure. I think, as you said, we may have to do a more detailed study on looking at what the actual different phase domains look like, and then try to model resistances that way.
Right. That could depend on how phase separation really happens in reality, and there may be you know, so one may wonder whether the fact that your experimental resistivity is actually significantly higher than the rest. It seems to be almost an offset. Maybe these are grain boundaries, for example, or something.
That's true, and also the experiment is not is at room temperature.
Oh,
So
I see.
and
see.
our calculations are DFT calculations, they're 0 Kelvin. So I think that will give an. I
see.
think that's mainly the offset.
I see. Good point.
Yeah. So yeah, but certainly defects, grain boundaries, all these things will have an impact.
So these pictures of the experimental results are all done at room temperature, not at low temperature.
Yeah, they're all done at room temperature.
Okay, because what I was thinking of when you look at in the FCC phase,
Yeah.
I was surprised that the CPA apparently seems to mimic the experiment, when typically what we have found is that using these kinds of techniques that you typically underestimate the zero temperature resistivity, and that can be quite large, right?
Yeah.
So again, it would be nice to I mean, when do the experimentalists approachable and say, why can't you do some measurements at zero temperature just to see how? Because you've got two things, right? You've got the disorder and you've got lattice vibrations, right?
Yeah.
And it's difficult to separate those without experiment or you putting something in to do with the lattice vibrations.
Yeah, that's
Actually, you know what also comes to mind is that maybe I mean, DFT codes will normally give you phonon. You can get phonon band structures from DFT, and also the electron phonon coupling constants often can be easily extracted, and then one can just do the standard phonon calculation, which basically linear is in metals. It's linear resistivity. All you have to know is the phonon, basically the bifrequency and the electron phonon coupling constant. Then you can estimate what is the contribution for, you know, for contribution from phonon scattering can be easily estimated, at least, you know, at the level of, you know, a rough estimate. So I think maybe that's what we're doing, perhaps.
Yeah, I mean, it would be interesting to try to incorporate those effects. Okay, so yeah, so there is one example. So there are many examples of alloys people have. So there are maybe not many for high entropy alloys, but there's certainly, so there's a good one on Cantor-Wu systems. And then there are plenty of CPA studies on binary alloys. So that is a sort of well established, and many people have done studies. Something that's less done is trying to calculate random alloys using a supercell with LSMS. So you can, instead of taking an effective medium, just take a really large cell and then try to apply the Kubo-Greenwood equation there. So the method would be to use the locally self-consistent multiple scattering method, or LSMS. And the idea is, if you have a random system, then the correlations do not exist to a very large distance. That means beyond a certain radii, you don't need to calculate you may not need to calculate tau matrix. It may not be that important. So as a result, for each atom, you specify what's called the local interaction zone, the LIZ, which is characterized by an LIZ radius. So for all atoms within that radius are taken into account when you calculate the tau matrix. So you are including scattering between those two when an electron scatters between those two scattering centers. But beyond that LIZ radius, you don't take anything else into account. And by doing that, calculating the tau matrix, which is generally an n cubed operation, because it involves some matrix, big matrix inverse, it becomes an order n operation, because you're not really inverting a matrix associated with the entire system. You're inverting a matrix associated with the LIZ size. So this is a huge simplification in terms of computational complexity. So
Can you just explain here a little bit? If my understanding is correct, this is very similar to what people call, and a lot of work has been done by Gerald's group and by Anya and other people, Hannah and other people, which is like a cluster version of CPS. So if outside this circle, do you have an effective medium outside that circle? How do you exactly treat the atoms outside the circle?
So you can have an effective medium, but for now we just have vacuum outside the.
Or just vacuum, I see.
Yeah.
So in some sense, this is like assuming that would be like saying, but doesn't it have a periodic boundary conditions or just open boundary conditions?
So it has, so in the LIZ calculation, it certainly has, it has periodic boundary conditions. So for if you look at this black atom at the right-hand side corner, when you calculate the LIZ for that atom, you will take into account this red one that's to the left. So when you calculate the tau matrix, there will be periodic boundary conditions. But there's, yeah, there will be, but it's an entirely real space method. So there's no K-space involved.
Right, but what's really nice, so this is really telling you there is a certain kind of correlation length, or there is a certain length over which you have significant correlations. And so by doing this, you can really see how big the system do you need, right? Is that correct? So
yeah, that is correct.
You can tell, right?
Yeah, and in fact, I'll basically in some of the conductivity results, that plays a big role in what LIZ size to take to ensure your conductivity is converged. So that I will show some plots on that. And yeah, so the idea is to essentially, well, use this method because this can deal with supercells efficiently, and we can and also you can deal with randomness better here than CPA, because you can deal with systems where your atoms are displaced from the ideal lattice sites, which can be done with CPA as well, but it can be done much more easily here. And you can deal with, you're not constrained by the simplicity of an effective medium. So essentially you can, it's a very simple direct method. So you have this equation 8 that I'd shown previously. You just get rid of this ensemble average because you've taken a large system, which is sort of self-averaging, and you just sum over M and N over which are the site indices. So you just sum over, you just calculate the tau matrix for the system, you calculate the current matrix for each atom, you literally just multiply them together and you sum them up. That's the very simple idea. And so what you end up with is equation 9. So for each, you're summing over each site shown by the index M. And for each of these sites, there is an LIZ. So you sum over all the atoms within the LIZ of that site, which is shown by the sum N. And then you calculate the corresponding matrices. And we implemented this in MUST. And basically, that's what I did during the summer, implementing this method and then trying it out on different systems. So a little more details on the implementation. So there are two main parts, computationally speaking, which take time. So one is constructing the LIZ tau cluster. So this is a big matrix, and you have to take inverse of this matrix, and you have to do it for each atom because each atom has an LIZ. So this is where most of the time is taken up in the calculation. And this is our biggest bottleneck right now, which is what we're working on, making it faster. And also constructing the conductivity sum, because once you have all these matrices tau, you have to then multiply it with the current matrix and then do a double sum over M and N. So this also takes some time. Both of these things are parallelizable. So you have a loop over all the atoms that can be dealt with either MPI or OpenMP, and then your inverse can be offloaded to a GPU. Again, which is the implementation of which is what we're working on. And although currently all the results I'll show have been done sequentially using just one processor, because we wanted to ensure the approach works and we're getting something physical. So now we're working on how we can scale this up. So the first system I did was pure lithium. And so we looked at the 0, 0 element of the tau matrix with the LIZ radius. So basically this shows how the scattering matrix decays as the two atoms between which you're calculating the scattering matrix get further and further apart. So you see a nice oscillation to which we can fit this function quite well. And we also found it interesting that the fitting parameter we got here seems to match the Fermi wave vector KF well, although we didn't get that kind of match for other systems. So the next step was the main
Before we go to the
takeaway.
next step, what the denominator has R to a power which is not 1 or something else. Where does this power come from? I think.
So I think this is basically the implication I took from the power is, so you have to multiply this tau twice. So basically in the conductivity expression, it's like 1 to the power of R 2.8 roughly. And if you integrate that over all volume, which is what you're essentially doing in the sum, it will not converge because you need minimum 1 over R cube in an integral over volume for it to converge, which means the conductivity will not converge, which is what we expect because it's a pure element. So that's the implication I took from that. But otherwise, there's no there's no formula. We just thought this function might fit well. I mean, there's no.
It's just that what comes to mind is that if you do have a disorder and not a pure system, but then you have an atom surrounded by something else, then it's like an impurity, and this impurity will create Friedel oscillations. This seems reminiscent of the Friedel oscillations that are created by the impurity in some host. Now, exactly what this is, I don't understand, but I mean, there should be a connection to Friedel oscillation. This looks like Friedel oscillations that has the wrong power and stuff. Right?
Yeah, that's true. I mean, we have to look more at the physical reasoning for why this behaves like it. I'm not sure. I mean, when we plotted the data, we just thought this cos x upon decaying function might fit well with this. So we did a fit. So yeah, we are working on how to interpret this better. So obviously.
So you're calculating the resistivity, but this is a pure metal, right?
Yeah.
So where's the resistivity come from?
It shouldn't. It should be 0.
It's 0, right?
It should be. So
Yes.
which is so we did it as a test to see whether we get 0.
Oh, okay. Thank you.
Because since we know we should get 0, so the system acts as a good test case for us. So basically what we did is at different LIZ radius, we plotted the resistivity, and we're looking at whether as you go to infinite LIZ, you get the completely periodic pure element crystal, and it should be 0. And it's what we get. So you see when the 1 by LIZ goes to 0, this row seems to go to 0. Obviously, it would be nice if we had more data points here, but I've only calculated to the point where it seemed computationally practical to do so on a single core over a reasonable amount of time.
But it's funny because this looks like very much like a straight line, almost except extrapolating to zero. So it will be sort of interesting to to know how, if you actually fit it to a straight line and then you change the, you take the number of data points that exclude some, like the first 2 or 3 points on the right, you eliminate them from the linear fit and see as you're eliminating more and more, does this actually converge towards zero or something like that. I mean, this, at least naively, it looks like you really don't need to do very large cells, right? Even the straight line here, the slope starts at almost at the second point, which is kind of interesting, right?
Yeah, so basically that's sort of, so I took the log of both of them and I fitted that to a straight line. So that's the slope. So this is essentially almost linear.
Yeah.
So it does seem, since this is almost linear, that it's going to go to zero. But it would be,
Well,
ultimately it would be wonderful if we could just have a data point there which is zero. But
I mean, if I eyeball it, it seems to me that actually there's a tiny intercept if instead of doing log, because log works only if you actually know that it's going through zero, then you can use log.
Yeah.
But if there is a finite intercept, then log is not going to give you the power, right? Because it's not a power law.
yeah, that's true. It is, yeah, that's true. Yeah. So yeah, basically we calculated till the point where we could, and we seemed reasonably confident that it was going to, if not zero, then some really small value, which adds up with what we expect from the system. And the slow decay also makes sense because we saw in the tau plot that there was a slow decay of the tau. And if there's a slow decay of the tau matrix, there will be a slow decay of the conductivity. So, which means you...
Okay, so I didn't mean to interrupt.
Yeah.
Question. So lithium is has a very simple Fermi surface, right? It's just basically a sphere.
Yeah.
And so any scattering that you got is going to be the way things couple. If it's electrons at 2 different points in the material, then it's what dominates is the Fermi surface. And so is there a profit in looking at it from that point of view?
Yeah, I mean, yeah, it would be interesting to see the spectral function, and as it changes with the LIZ, and then try to see.
Yeah, I mean, at some point you're going to regenerate the Fermi surface, right?
Yeah.
Every atom's in there, right? And then you look how those states are filled. They're all occupied up to the Fermi surface and non-occupied afterwards. And so you're basically reconstructing, in some sense, that Fermi surface as you make the LIZ bigger and bigger and bigger.
Yeah, that's true. Yeah.
That's the sort of picture that comes to mind, anyway.
Yeah, that's true. I mean, it's essentially becoming more and more like a perfect crystal.
Yeah, because this becomes a perfect crystal. It's pure lithium, right? The zero temperature resistivity is zero. But anytime you muck it up by doing whatever, which is, you get the LIZ radius is in a sense mucking it up. It's putting some scattering in there that shouldn't be there. And as you get closer and closer to the Fermi surface, then you get closer and closer to T equals 0. The scattering is dominated by fewer and fewer electrons at the Fermi surface, right?
Yeah, that's true.
I'm not sure whether that's easy to do numerically, but it's just trying to come out with in the end, all this stuff is simple. The only problem is finding the simple answer, right?
Yeah, that's true.
By the way, my thesis was on things like this. So it's been, these problems have been worked on for a while.
Yeah, so we also looked at some other systems, basically some more pure systems, just to see whether we get a similar trend. So we looked at pure aluminum, which was a little worrying when we looked at the resistivity, because it really seems, looking at the plot, that it's not going to go to zero. But again, by doing a fit, the fit seems really off linear. So this is not a linear 1 over rho, and 1 over r are not linear, which means it will slope a bit at the end. But it shows a sort of similar slow decay, and it seems to be moving towards the pure element limit. We also did pure silver, pure copper, which is again given here. Again, the similar-ish behaviors all going to zero. So we seem somewhat satisfied with that it seemed to give expected results for pure elements within our computational constraints. So we thought, before we move on to trying to scale this and make it more computationally efficient, we should probably try some binary alloys, which is what we did. So for binary alloys, what you can do is you can play around a little bit, in that you can look at, so there's a big sum over j tau and j and tau, and you can break that sum into individual parts according to species. So you can look at sigma alpha. So you can only look at some terms where m is alpha and n is beta, and you can see what the contribution of that is. And similarly, you can correlate it with tau of the different species. So you can get some more information from this and sort of see whether it gives you something physical. So we looked at equiatomic aluminum vanadium, VCC. The reason for doing that is we saw from literature it has a really high resistivity, which means it should be, in principle, easier to converge and should not require a large LIZ size. So we looked at the tau, which broken down by species, which we found the vanadium to be the largest in magnitude. And also this is much faster decaying than the pure elements, which is expected because it's a random system. And we also found that the contribution to the conductivity is the largest for the vanadium. And we wanted to see why that is the case. And for that, we can look at the density of states for this system, broken down by species, so partial density of states. So when you see that, the vanadium density of states at the Fermi energy is significantly higher than aluminum because of d states. So hence its contribution, there are more states available for scattering. So it's the contribution to conductivity is higher. So that we thought was useful, because it means that the system, this method is not just giving you resistivity, it can also give you a species-wise breakdown, which could be useful. So that's another added perk of pursuing this method of calculating resistivity. We looked at the total resistivity with respect to CPA, which is an interesting test to see whether it would be comparable. It really seems that it's not converged at all. It seems to be sharply going down here, but then there's some oscillating behavior before. So I'm really not sure what the LSMS resistivity will converge to. So we have to go to a higher LIZ size, which means we sort of hit the bottleneck of this method, and that's currently what I'm working on doing, is to.
But this is the offset. I mean, this is it's not showing the entire vertical axis, so it's off by, well, it's off by 30%. basically from CPA, right?
Yeah, it seems that way. Yeah.
Yeah, I wonder if your unit cell is not large enough. You might have to increase the unit. How big is
Yeah.
the unit cell?
So I think this one was for 6x6x6. So what, 432 atoms.
400. You want to go to large? I'm afraid you have to go to larger unit cell.
Yeah, I found that.
Yeah, because when you increase the LIZ, it's going to you're going to include a lot of periodicity into your calculation.
Yeah, that's true. But I found that the LIZ size seemed to have a bigger role than. So if you take a good enough supercell, then the size does not play. I found does not play that big, and it seems to be the LIZ. But yeah, it would be. We are planning to take.
But you know, the reason maybe why this is so off from effective medium theory is that because outside your cluster, you're really not treating it in an optimum way, right? Whereas CPA does perform an optimum medium, puts an optimum medium. So if one actually did put an effective medium, like a CPA effective medium outside the cluster, then probably convergence would be much faster. This was the whole point of the so-called cluster CPA calculations that Gerald and others have developed, you know, that which can be done in real space or in momentum space. It doesn't have to be done in momentum space. So my point is that, you know, this convergence, which is pretty slow, is probably because you're not optimizing the medium outside.
That's true. Yeah. Yeah, that is. Yeah, that's a good idea to put an effective medium outside the LIZ.
Which I don't think is that hard. I mean, you don't have to optimize the medium in a fancy way. You could just put the CPA effective medium. You know.
Yeah, that's true.
Yeah, we'll be working on it. There's a method called a PCPA, polymorphous CPA. That's exactly what the yeah, that's what we intend to do, intend to implement. That method is being available.
Yeah.
Many years ago. Now we need to implement this.
Yeah.
Again, this resistivity is from what's experimental resistivity? Do you know?
So not for this. So for when we did calculations comparing to experiment, we got something that was like again similar 20% higher. The experiment.
Well, but again, in terms of the physics of resistivity of 300 micron centimeters means that you know, it's essentially the mean free path is the order of interatomic spacing. So it ought to be very very easy to do that, and that's probably why it turns out to be easier in this case for CPA than it is for doing this, right?
So Malcolm, can you actually elaborate a little bit about this? Because this is a topic that is very popular in many areas. This issue that when the mean free path becomes comparable to lattice spacing, this you offer a limit. So do you actually happen to know what is exactly the KFL here, or how can you? So you think micro centimeters will be?
Yeah.
Or how? What's your?
Yeah, I mean, you know, you get into the complications of the underlying theory when you get up to resistivities of the order of 300 micron centimeters. Well, less than that actually.
Right,
200 micron centimeters.
This is approaching million centimeters, really. Like it's a fraction of the million centimeter.
Yeah.
And so that's a pretty, yeah. It's. I see.
And yeah, I'm not.
Because that's exactly where, you know, things past CPA, they start coming like this multiple scattering corrections and localization or something like that, right?
Yeah, we considered this system because we thought if the resistivity is larger, then we might not need that big an LIZ size since the tau matrix will die out quickly.
Well, you know, it's not exactly, I think that's not exactly correct because, you know, in some sense, if you really want to form bound states, you cannot do this if you just have a local problem that you're solving. localization when you really form bound states. That's what, in fact, I wanted to mention that, part of the, I guess idea between when MAST was started with Gerald and Hannah and others. There are other methods that can be used, like this typical medium method, that can be actually used to put in back some localization in some way, in some simpler way. So maybe that's actually probably what becomes important once this. It's interesting, Malcolm, that you mentioned this CSI, that this is actually approaching that limit where CPA should not really work that great anymore.
Yeah.
Right? Yeah, that's a very good point.
Yeah. So for us, basically, we're kind of interested in seeing what happens when we go to smaller LIZ to see whether it goes to the CPA value or it converges to something else.
Well, if I take the last 6, 7 points on the right side, and if I linearly extrapolate them, I actually get something not too far from CPA.
Yeah.
I'm looking at my computer, right? Like it's sloping down, right? It seems to almost, right?
Yeah, but there's some sort of oscillatory behavior in the resistivity.
Okay, yeah.
Because as you consider, since there's randomness, and as you consider more and more neighbor shells,
For
it
sure,
seems to be
Yeah.
Okay. So yeah, basically the next steps, what I'm currently working. So Marcus Eisenbach has a C++ high performance code for LSMS, and I've implemented this method in the Fortran and the C++, and I'm working on making it faster, essentially, so it can then run on Summit and can produce results at very high LIZ. And then we can resolve some of those plots that I'd shown before. Also, a big advantage of doing this approach as opposed to CPAs, you can study systems like metallic glasses and quasi-crystals, where there is significant displacement from ideal sort of a periodic crystal, and incorporating that in CPA is harder. And so on left is some calculation that I did for a quasi-crystal structure that was given to me by my advisor. And these are, of course, absurdly large, but I looked at some experimental resistivities for quasi-crystals, and those are pretty large as well, of the order of 1,000 micron centimeter.
Right.
So basically, once the high performance code has been implemented, we will try the system. This was a test I basically did to see whether I would get something unphysical, or whether the code crashes, or but it does seem to give something not too bad. So
I would like to mention something maybe one should keep in mind, is that this strong dependence on the cell radius is telling you that there are multiple scattering processes, which are some kind of interference processes. Now, these require phase coherence. And when you do zero temperature calculations, that phase coherence is given. But at finite temperature, there are some inelastic scattering events that could reduce the phase coherence. And in fact, I happen to know that in quasi-crystals, it turns out that if you go to a finite temperature, you can actually increase the temperature and reduce the resistivity in some cases, which was claimed was strange, but it somehow gets, it's consistent with the idea that these multiple scattering processes are increasing the resistivity, and once you suppress them by finite temperature fluctuations, then you can reduce the resistivity. But I'm mentioning this because if there exists an inelastic mean-free path, which is finite, and maybe becomes shorter at high temperature, then maybe the cell radius that you need will not be so large. In other words, there can be enhanced convergence of this code if you had inelastic scattering, which is not currently included, but it's possible that in some systems, especially in strongly correlated systems, inelastic scattering can be significant, and then the convergence will be much faster. So maybe one should keep that in mind. It may depend on the system, but
yeah, that's true. That's something we'll consider. Yeah. Okay, so basically here's a summary. You can deal with disorder using
Can I just go
CPA.
back? Can I just go back to the previous thing? So in this thing here, you've got a LIZ size, and you've got a well, you've got an. But did I understand that you've still got a periodic object, right?
Yes, it's a quasi-crystal approximant. Yeah.
Yeah. So at some point when you make your LIZ larger, it hits the boundary of the number of atoms you've got in the system, right? Number of atoms you've got in the system is
Yeah, it does.
it shows, right?
Yes.
So once you get the LIZ size to that size, then the system starts to know, oh yeah. I'm not a I don't go on forever. I go on to a certain size, and then I have periodicity.
Yeah, I see what you mean. Yeah.
And in these calculations, where are you on it when looked in terms of those parameters?
So basically what we expect is things will look like is there will be a point where you increase the LIZ where things will converge, and it seems like it's not changing much. And then when you increase the LIZ even more, it should start to go to zero, because as you said, you're looking at a perfect crystal again, because it's periodic.
Yeah, right.
And any periodic system at 0 Kelvin should give you zero. So ideally, we're looking for the sort of sweet spot in the LIZ, which is after the period we're currently at, where there are some oscillations and you don't know what's happening, and before the period where it's deterministically going to zero.
Mm-hmm.
So that's what we're looking for. There should be a sweet spot in LIZ where it's sort of flat and not changing, and that should be the random resistivity.
Okay.
Well, I think Malcolm is right that, in principle, for this method to work, the saturation with increasing LIZ should occur before you hit the system size.
Yeah.
Because obviously, once you go past the system size, it's going to go back down. So if you can kind of converge to something flat before you hit the system size, then you can feel good about it, right? If you just see the maximum at the system size, then you didn't learn anything from this, right?
Yeah, hopefully we should see some sort of flat resistivity, and then before this is the system sees periodicity.
How big is your system here in this case?
It's about 500 atoms.
So in linear direction, if you take a square root, cube root of 500 atoms, what is that? That's like, what's the cube root of 500?
About 8.
Right. So you know, the Liz radius cannot be much larger than 8, right? Isn't that, Malcolm, what you're saying, right?
Yeah, that's right. Mm-hmm.
Yeah, I think the current constraint is the code is this conductivity calculation. The code is not parallelized. That's why he cannot go beyond too large user cell. We hope that once the code being parallelized, and we'll go large user cell size. We shouldn't go to like a tens of thousands. That's
Right.
Yeah.
But Malcolm made a good point. Is that this? It doesn't make sense with such small system size to go to Liz radius, which are too big, right? Because then you get periodicity.
Yeah, it's true. I mean, this is essentially, I'm just going to large LIZ size to see what happens. So yeah, that is. I mean, I completely agree with what you're saying, that it should. It's a periodic system, and if you go to large enough LIZ, it should go to zero.
Yeah.
That's true. But since there's randomness in the system, that would complicate things, and the idea would be to see how the randomness is complicating things.
To get it to go to zero, you have to go to a size, at least radius, which is many times your system size. Right?
Yeah.
Which that is impossible. So I don't think it's very hard to get to that limit, right? Where your resistivity will go to zero because of periodicity, because periodicity has to be developed, right? If you have one or two system sizes, then you're obviously not in the regime where that works, right?
Yeah, that's true. Yeah. Yeah, so essentially, you can do it with CPA, you can do LSMS. We've already done CPA before, so this time we're trying to do LSMS, and we saw for pure elements, it seems to give an expected behavior where things are going to zero, and there's a slow decay. And for aluminum vanadium, when we break it down with species, we can see some expected behavior. For example, the vanadium contribution is higher, as indicated by the density of states. But if we really want to see convergent resistivities and sort of more theory on what actually happens at higher LIZ, we need to then parallelize the code. And then that is sort of what we're working on. I'll just slightly skip ahead because so I now moving completely away from this to a different project, which is previously I had presented one of our research projects where we were calculating VASP, MUST, and WIEN2K for a set of BCC and FCC structures. And the idea was to see whether you would get consistent results, because these three codes use three different techniques to calculate your energy. So WIEN2K uses the full potential LAPW method. VASP uses a pseudo potential method where they have a frozen core, and MUST uses the KKR-Green's function method. So there are three completely different approaches, and we want to see whether they give similar results. And to do that, we have 6 BCC structures and 4 FCC structures of different symmetries as specified here for binary alloys. So the two systems I'm interested in looking at is chromium niobium and chromium vanadium. And I calculate the energies for 6 chromium niobium structures and 6 chromium vanadium structures of these symmetries using the 3 different codes. And I plot it and see what happens. So here's the comparison. So on the left, you have chromium niobium. On the right, you have chromium vanadium. Now, the most remarkable thing is the muffin tin is incredibly wrong for chromium niobium. So the muffin tin shows a much higher energy difference, relative energy difference than what it actually is. And that's not really the case for chromium vanadium. There's a much smaller mismatch. The full potential seems to perform well for all the systems. There's a slight mismatch here of the order of a few millirudbergs, which I think is due to the semi-core treatment, but we've not really gone into that. But what we want to see is, so why is this muffin tin working so well for one system and really badly for another system? And one way to try and understand that is to plot the potential. So in the full potential calculation, in the output file of MUST, it shows you the radial parts of the potential resolved according to different LM indices. It should be easy to then get that, multiply it with the required spherical harmonics, and then plot it to see the angular variation of the potential. So, which is what we've done. So A and C are 2 different symmetries for the chromium niobium, and B and D are 2 different symmetries for the chromium vanadium. And we found that there's an asymmetry. So it's plotted with respect to the phi and theta angle. So you're plotting it on the muffin tin sphere. And it seems that for the chromium niobium, you can quite easily pick out the 2 different species. And in fact, this variation also shows you the symmetry. So this alternation in C, one could imply that this is a CF16 type structure, which it is. And here from A, you can see that there are similar layers of one structure, one species, and similar layer of the other. So this is a TP8 structure, I think. So you can actually see that just by looking at the potential plots. Whereas for chromium niobium, you can't really see that. It's a lot more similar, the potential of the 2 different species. So for chromium vanadium, so it shows that the anisotropy for chromium vanadium is a lot lesser. The variation along the species along the theta and phi, whereas for chromium niobium, it's a lot more stark. So this gives us some intuition on why the muffin tin approximation works quite well for chromium vanadium, and it works poorly for chromium niobium. And a similar thing can be seen for FCC structures as well. So if you make a similar set of FCC structures with different symmetries, you can see the same thing. It's also, I thought interesting that chromium vanadium are next to each other on the periodic table. They have a similar, almost identical atomic numbers, whereas it's quite different for chromium niobium, and I feel that could have an impact here. Also, Yang mentioned last time about radical plane ratio. So Yang had shown how if you vary the radical plane ratio, you can get the correct band structure for silicon using MUST, which is a sort of long-standing problem that MUST couldn't give correct values for silicon.
It's 11 o'clock.
So I thought it would be interesting to vary the radical plane ratio between the two species to sort of set it similar to the atomic radii of chromium and niobium, and to see whether or nickel and palladium as given here, and see whether that would have an impact. So for chromium niobium, it doesn't have an impact really. So changing the radical plane ratio doesn't solve the issue at all. But for nickel palladium, which is an FCC structure, initially, if you look at the muffin tin value with a radical plane ratio 1, which is what it is by default, the mismatch is bad. But as you increase the radical plane ratio, it then approaches the VASP and WIEN2K value, and between 1.1 and 1.15 is where you have a sort of match with VASP and WIEN2K, which is also quite similar to the atomic radii ratio if you take between palladium and niobium, palladium nickel, sorry. So basically this shows that the radical plane ratio could be an important factor in muffin tin calculations. So you may not have to go to full potential all the time. You can vary the muffin tin. You can try different radical plane ratio, and muffin tin may be giving you good results. Yeah, so that's basically the updates I had on this project.
Okay. Any questions? Okay. You also mentioned about this the different treatment of it. Looking at the difference between full potential result and the WIEN2K and the VASP.
Yeah.
Certainly, there's a different treatment of semicolon states.
Yeah.
So in some semicolon states in the system in WIEN2K and the VASP, they're treated as valence electrons, but
Yeah.
in the MUST, so but they're treated as a semicolon states. The way they're solving them is just different. So I think that might be the difference causing it.
Yeah. So I think we tried some calculations and there was some impact, but I think we were having some convergence issues with MUST and semicolon.
Mhm.
So I mean, we could also take a really big contour and ensure that your contour is big enough that it covers the semicolon states, and then that automatically treats your semicolon as valence. But we found that is really inefficient and was giving some wasn't really converging well.
Yeah, what's the situation with Dwayne Johnson and his? I mean, he has this very simple different sphere sizes, doesn't it, for different elements, and he's always arguing that he gets very, very good answers, but I've never done anything with that, and I just wonder if you know where what Dwayne does stands, because it's basically just ASA in the end, right? Atomic sphere approximation.
Yeah, my understanding is they are working on full potential KKR code.
Yeah.
And what they do is each iteration, they're going to check the extreme value of the electron density between two atoms.
Mhm.
So they'll put the radical plan just right at that point.
Right there. Yeah. Mhm.
So that's what. So they have like a just adaptive radical plans.
Mhm.
Yes, I think this is a good idea. We may borrow, but they could be set up this for their ASA also. That's the way they do. Obviously, from Vishnu's result, you can certainly just do Morphin calculation with with appropriate radical plan. Given each atom a different atomic size.
Yeah.
Then you
Right,
achieve
right.
the excellent result.
Well, and the radical planes construction preserves it preserves volume, right? Guaranteed. Yeah, it is right.
Yeah, just I guess it's reasonable to explain what a radical plane is to for those who are not familiar with this. When you construct a beta size cell in the textbook problem, if you have a same atom in a crystal, you put a boundary plane between two atoms just right in the middle. That's how we construct beta size cell. But you have two different species or different species. Putting that plane in between two atoms, it becomes unreasonable because some atoms tend to be larger atomic size than the other. So where do you put that plane? That become an issue, right? So
right.
that's the argument here. Where do we put that
Yeah.
boundary between two atoms? Okay, thank you very much, Vishnu. Let me stop. There's a chat. Let me stop recording. Oh, Franco asked, did you calculate everything with LDA?
That's a good question. I calculated with PB and I repeated everything with LDA, and there was no difference.
Okay, let me stop recording.